let's chat about vectors. A vector is characterized by a magnitude, so a size, and a direction. There we go. Direction. So usually a vector is drawn as an arrow where the length of the arrow is the magnitude. Okay, so let's say we want it 4 units, and the direction is the direction. So I've got an arrow, it's 4 units, and I don't know, it's northwest, right? So two vectors are equal if and only if they have the same length and the same direction. The same magnitude and direction. Fair enough? Okay, so which vectors are equal here? Let's see. So these two have the same magnitude, but they don't have the same direction. This one is going sort of, for lack of a better word, southwest. This is going northeast. So these can't be the same. These two can't be the same. These have more or less the same magnitude. Those three have the same magnitude. But only these two have the same magnitude and same direction. Okay? Now, usually we're not just looking at pictures. Typically, we denote vectors either as a script boldface or boldface with an arrow over them, or sometimes as an ordered pair. Actually, perhaps I should also mention our textbook's going to favor that notation. Sometimes people write them with angled vectors also. Now, the magnitude of a vector, if you have a vector AB, okay, we can denote as the square root of a squared plus b squared. And hopefully that makes a lot of sense to you. You know, if your vector, let's say, since any vector is equivalent as long as it has the same magnitude and direction, if we were starting it at the origin, that would be a safe assumption. This would say we'd go over A, we'd go up B, and we want to know what the magnitude is, right? We want to know what the magnitude of this thing is. And so we'd use a squared plus b squared equals c squared, right? So what's the direction? Now the direction, and hopefully this actually rings a bell in your memory about polar coordinates. The magnitude looks very much like the radius, and the direction looks like the theta in polar coordinates. Okay, so the direction is tan inverse. If you had the a and the b, how would you get this theta? Tan inverse of theta, right? But what should we say? Plus pi or plus 180 if a is less than 0, right? Tan inverse does a great job of taking care of quadrants 1 and 4. So that would be the angle. Oops. Sorry, tan inverse of b over a, remember. So this, we have tan of theta equals b over a, right? The tangent of that angle is the slope. So tan inverse of the slope gives us the angle. Well, that's going to tell us about this, but if we should happen to have a less than 0, let's say we're in quadrant 3, we have to add pi to get from what tan inverse gets us to there. So you're going to have to use some common sense to know whether you add pi, or if you're in degrees, you're going to add 180. Okay, last piece that we want to deal with in this video is addition and subtraction of vectors. If the vectors are written in this form, life is just grand. What do? We add the x-coordinates. And this makes perfect sense, by the way, if these were two different forces, right? Forces have magnitude and direction. For instance, if gravity was pulling in this direction and the wind was blowing in this direction, well, the x-coordinates would combine. So you'd have 2 plus 1 in the x direction. And the y-coordinates would combine. Minus 3 plus 2 is minus 1, okay? And I included some chart paper over here so we could sort of highlight what this looks like. Okay, 2, negative 3, over 2, down 3. That's what the first vector would look like. And you could start this right at the origin, but to emphasize that we're putting these together, I'm going to start it actually here. Okay, I'm going to go up 2 and right 1. And so the upshot here is actually the composite vector. This is what addition looks like right there, okay? You could do it the other order, right? Addition is commutative, so you could go up, and then you could go down. You could think about subtraction as changing the direction of the arrow, and life would be grand. But this is this vector plus that vector. That's the composition. Now, often you don't have things that are integers in vectors. Addition and subtraction works just the same way. 2 minus square root of 3. You can just leave that in the x-coordinate. Pi minus 1, you can leave in the y-coordinate, and that would be the difference of the two vectors.